Yeah, it's really nice to be here. Thanks for welcoming me. My name is John. Just a quick intro of myself. I'm currently first year at Stanford, advised by Ludwig Schmidt and Dee Yang. I used to be a master's student at Princeton, working with Karthik Narasimhan. And I've mainly been doing work in the coding agent, software engineering agent space. If you haven't heard, some of my prior works that I led and did include SWE-bench, SWE-agent. I also did some web navigation stuff before that, and Intercode, along with all of the spin-offs that maybe you've heard of, such as SWE-bench Verified. Cool. So today my talk is going to not be about evaluation, which was sort of the theme a year ago, but more about trying to train models that actually perform well on this benchmark. So if you're not familiar at this point, to set some context, one of the more popular evaluations for testing models as coding agents or as software engineering agents is this benchmark called SWE-bench, which takes GitHub issues and PRs and this kind of issue resolution workflow in the real world, and then reformulates that as a problem. So you're given a code base along with some sort of issue presented in natural language, and the system, whether it's sort of a language model that's digesting the entire code base or working through a scaffold like SWE-agent or OpenHands, if you've heard of these ones, is going to then make modifications to the code base that attempts to resolve the issue as described in natural language. And then to verify whether the fix is good, you're just going to run a couple unit tests. So there's been a lot of progress since this benchmark was first released a year ago. If you are up to date with the leaderboard, if not, you can check out SWE-bench.com. We basically went from models doing like 2, 3, 4% on this benchmark to now achieving scores of like 70, 71. I guess GPT-5 is going to come out this week, so we'll see what the new number is there. But a lot of these sort of big jumps in performance are due to stronger models. So that kind of begs the question from an academic standpoint of just like, how do you actually make better models, particularly thinking about it from a data perspective. And ever since like earlier this year and around last December, there have been efforts to kind of create better data sets and more environments and more sort of training grounds to build better software engineering agents. And there have typically been kind of two flavors. So they're both kind of shaped by the two dominant approaches to performing well on SWE-bench. One of the approaches we've already talked about is agentic, right? Like you take a language model, it's given the issue, and then you put it through a number of these kind of react, reasoning, act style interactions. So it's going to say, okay, maybe I should open this file first, and then it does like a bash, like open command or ls command if it wants to see the files. It issues that tool call or that bash command if you're working in a CLI, and then you get the standard output from the terminal as your observation, and you just kind of put it in that setting. Another approach that is noteworthy, but I think the agent approach is still is starting to pick up a bit more steam, is this kind of agentless setting where you don't need execution, you don't need an agent interacting with an environment. There are these frameworks literally called agentless, which allows a model to kind of solve the software engineering task as a math problem, if you will, where it's not really like running Python or running anything against a CLI. It's kind of looking at the code semantics and then thinking really hard about what the modification should be. So when it comes to actually creating training recipes for these two types of methods, you run into different kinds of difficulties. So for the agentic approach, what some prior work has done, such as SWE-gym, is literally just redo the SWE-bench collection pipeline, but on a different set of repositories, and designate those as training repositories. Now, why is that tricky? I'll talk about it really quickly. The other form, like SWE-fixer or SWE-RL, simply crawls like large swaths of PRs from online. So what's kind of missing in these existing recipes? So if you are to think about the kind of agentless approach, you can crawl a lot of PRs, but really ultimately you're training on the surface forms of these of code. You're not really interacting with it. You're not running commands, you're not seeing execution output. And so fundamentally, that paradigm can be kind of limiting. And so those data sets are very scalable in the sense that you can certainly crawl a lot of PRs online, but there's not that much that you can do with that kind of data. On the other hand, with SWE-bench or SWE-gym, one of the good things there is now you have an execution environment. You have something that you have a language model be able to run against. It's very transferable, literally. This is the kind of stuff that you and I would do on our laptops. But collecting these execution environments, and if you're not familiar, I recommend checking out the SWE-bench work, is highly manual and really tricky. The core problem being that you need to download a repository, check out like that version of the repository from like 2 years ago, which corresponds to that PR, and then figure out how to install that repository at that version. And you can imagine there's just like a whole host of problems that come up there. So it's very tedious. It's feasible, but it's very manual. So the goal of this work is to try to get the best of all of these worlds and create a strategy that allows you to scale to a lot of repositories automatically and synthesize a lot of task instances in those repositories, right? So just to rehash, the core sort of problems requires a lot of human effort to install like repos from a year, 2, 3, 4, 5 years ago. Each of the instances also has its own Docker image. So an environment, when we're thinking about the SWE-bench setting, we're just referring to a Docker image, right? And that image, inherits from some base image. It clones the repo, sets it up, runs some installation commands. Each of these things can amount to 1 to a couple gigabytes of storage per instance, and that's like at least academically, that's a fairly high cost to pay. And then last but not least, with SWE-bench, it's a great evaluation because it draws from real world PRs, but in some sense for training, you can also think of that as a limitation. You're kind of confined to like whatever is out there in the world. So thinking about this is where we introduce SWE-smith. So the goal of SWE-smith, before diving into it, is, as we mentioned, we want a lot of repositories, hundreds of repositories and thousands of task instances, and we want to be able to scale these things with little to no human supervision. And that's what we try to achieve here. So basically, the idea here is that you can semi-automatically use an agent to install a repository. And then once you have an execution environment for that repository, you can come up with a lot of strategies to then synthesize bugs in the code base. And then effectively, you get this great training set where you have thousands of instances with execution environments that you can then throw whatever training algorithm you want at it. So basically, concretely, these are the 3 workflows that we enable. You have a GitHub repository, you want to create a Docker image / execution environment for it. Given this execution environment, you then synthesize task instances. Now what that means is a task instance is kind of a delta to the existing code base that would break 1 or more existing unit tests. So what that means is in the original version of the repository, let's just say you have like 100 working unit tests and they're all passing. You can create a task instance by screwing up the code somehow such that maybe like 5 of those tests don't pass, right? And then last but not least, you can train, and that's kind of like where, even today, you can imbue a lot of your creativity. So the first step is pretty simple. If you're not familiar, the project that I did right after SWE-bench was SWE-agent, which introduced this kind of paradigm of how do you get language models to act as an agent and solve software engineering tasks. So it's been refined and improved a lot over the past year, and now it's good enough such that if you give it a GitHub repo, you can just ask it to try to install the repo, and there's like a 40% success rate there. If you don't know what SWE-agent is, you can just ask Claude Code essentially to do the same thing. So now that you have an execution environment, this is where you can have a lot of fun. So now we're in the setting where you have the code base. It's like the latest version of NumPy or Tensor, whatever your favorite code base is. And you've run it and you've seen there's like n passing tests. You've run the test suite like PyTest, and you can see, there's a good test suite here. So now what we're going to do is like using a variety of methods that vary in both their cost and the complexity of the method, generate changes to the code base, logical changes that then cause like 1 or more of those existing tests to fail. And I'll just kind of speed run through the techniques here. So one of them that's just completely free of cost is what we call procedural modification. So beyond the name, really it's a very simple concept. You take a function or a class or some programmatic entity, and then you turn it into an abstract syntax tree. And there's a lot of great libraries for doing this. When we did the original project, we just focused on Python, but we've recently expanded to like 9 other languages. You take the AST, which is this kind of nice, structured representation that allows you to kind of like not have to deal with very specific surface form semantics, and you do random manipulations. You can remove an assignment, you can like flip the conditions and an if conditional, you can like blank out certain for loops or whatever, stuff like that. There's a lot of things you could do here. And then you like convert that mutated AST back into source code, and that source code is going to reflect some sort of change. So this is a really good strategy for defining kind of like structured large numbers of bugs that are sort of, of some particular characteristic. Another simple strategy is to use a language model. So there's 2 strategies here. Either you give it the original function and you ask the language model like, hey, screw it up. Or something that we found to be more effective is that you blank out the function and you ask the language model to re-implement it. And anytime it does it wrong, you can keep that as a task instance. All of those previous methods, you might have noticed, will typically edit one programmatic entity. So what that means is it's like usually changing one function or one class within one file. If you look at SWE-bench or just any good distribution of real-world PRs, you'll find that typically there might be multi-file changes. It's not just kind of limited to one specific part of the code base. So in order to emulate that, you can be smart about combining different bug patches that we just kind of talked about from the previous 2 strategies, whether they're like from the same module or if they break the same test or if they're from the same file. By no means is this like sort of supposed to be completely comprehensive of every way you could create bugs, but this is a really good strategy to get more complex changes. And then last but not least, all those methods are synthetic. With SWE-smith, you can also kind of preserve the real world goodness that SWE-bench has. And the way that you would go about doing this is you give it a PR for that code base, and you essentially ask it to undo the changes that that PR did for that code base. So it's basically, simply put, a much less manual way to do SWE-bench style collection. But all of these methods, basically the idea is that the input is a code base and the output is a diff that breaks some tests. So whatever the method is, if it's interesting, you can explore more methods. You're just creating this. It's just a set of changes that somehow break the code base in one way or another, which really is the essence of SWE-bench. So SWE-bench is 2,294 task instances. The most widely used subset, which is SWE-bench verified, is 500 task instances. Something like SWE-gym was 2,000 task instances, and they're all from like tens of repositories. With SWE-smith, we're able to scale this like 10x in terms of number of task instances and number of repositories represented. And you can kind of look at the paper if you want more statistics. But something that, and there's sort of a nice little chart of like, given the same number of repos, how many task instances can you expect to get? Okay, I guess it's not highlighted. Something else that I wanted to highlight that's mentioned in the paper is that the storage cost is way lower. So for SWE-bench, it's like 1 Docker image or 1 execution environment per instance. In this case, it's 1 execution environment per repo. So it's just a lot more efficient in terms of, what execution environments you need to represent how many task instances. Cool. I'll skip over this slide because I'm running a little low on time. Oh, and then the right-hand chart for this is where you kind of see what the difference in storage is. Cool, and then last but not least, you can train. So this paper was released like 3 months ago. At the time, we were still doing basically distillation and like rejection sampling fine-tuning. So you just take an expert model with SWE agent, like Claude 3.5 or 3.7. You generate a lot of trajectories, and then you just fine-tune like a student model, like Quen 2.5 on it. And as part of this paper, we also just introduced another evaluation called SWE-bench multilingual. Certainly not the highlight of this paper, but then it gave us a sense of like performance like outside of the Python domain. So it's the first model, I mean, now there's much more, but it's the first model to crack 40% that's like completely open data and open source, although it is based on Qwen 2.5. So I guess the fine tuning is open source. And there's like a lovely chart here, sort of just bragging about it. And then there's some sort of nice scaling laws here. So like, well, I guess scaling trend, I won't say scaling law, where just the more trajectories is better, and it hasn't really plateaued yet to our knowledge, yeah. And then there's a bunch of ablations. Basically, I think as people progress and make better coding agents, I think it'd be really cool to see works that think about this more academically or more sort of in a principled manner as opposed to just throwing a lot of data at things. So for example, like simple things like increasing the number of repos represented or the types of bugs that are there is super, super helpful for making the model better. And you know, I'm a little low on time, so the other ablations are interesting, but I'll skip them over for now. One thing that's kind of neat that we played with is that if you take a 7B model and then train it on a bunch of trajectories synthesized using SWE-smith for just one repo, you can get a 7B model that is very, very competitive with, you know, a state-of-the-art model for just that repository. So effectively, what I'm trying to say is that SWE-smith enables like hyper good agents on one repo. Whoops, sorry. We did this with the DSPy library from Stanford, and at this point, like, you know, people have started training their own kind of repo-specific agents. So there's a couple like pretty awesome follow-ups, like SWE-bench, SWE-agent, SWE-smith is like, it's a big community now, so if you're interested, you know, we'd love to see you participate. But yeah, more repositories, more languages. When we initially released the paper, it was on 128 Python repositories with 50K task instances. We've now supported 9 different programming languages, and we just generated 10K more task instances for Go, and we're actively trying to increase this for all the other programming languages. You know, you can think of new ways to generate bugs or issue text. If you've seen like the Qwen 3 coder stuff come out recently, or the great work at Berkeley like SkyRL or DeepSWE or Agenica, they're all using SWE-smith at this point. So I think this is sort of a very exciting data flywheel that's, you know, there's very obvious things to contribute to here. And then I think the one repo, one agent setting is potentially quite interesting. Maybe there's new research questions to ask there. But yeah, I mean, there's a whole ecosystem at this point that me and, you know, my collaborators at Princeton and Stanford have been working on. SWE-agent, we just released mini SWE-agent last week. SWE-bench, SWE-rex, SWE-smith, it's all SWE stuff. So definitely encourage you to check it out if you want to work on evals or agents or data. Like, you know, this is a completely open source ecosystem. So yeah, we would be very excited to see you there. But yeah, I'll leave the remaining time for questions.
Not really work. Oh, okay.
Thanks. That's really interesting. And I just had a little bit of a somewhat philosophical question about building agents like this. It seems that the evaluations are all on whether you close the issue or solve the bug at the high level.
Right.
As a software engineer, I think you have a sense often that the quality of the work is based on the very, very granular details of how the person or the engineer is thinking about each piece. I was wondering how much you pressed on sort of reproducing the very, very detailed thought process behind PRs and then validating whether they are actually true against like libraries and tools and things like this. Because my experience, the coding agents tend to fall off when they have inaccurate, you know, detailed granular steps. So I was wondering how you balance the granular training data from this issue level training data.
Yeah, I think that's a great question. Yeah, I think maybe one way to think about that is like, is unit tests even a great signal? It's sort of very terminal, but what about the process? I think this is like exactly why a lot of the existing RL efforts are starting to use SWE-smith, because you can kind of define your own problems and then examine those things. I don't think I necessarily have the right opinion on this, but I agree your question is really interesting. I'm not sure what the appropriate sort of process reward is here. I think some papers have shown very simple things like checking whether the model identified which file to edit, even if it didn't get the edit right, or kind of these sort of more specific steps. It seems to help. But also at the end of the day, compared to just a sparse reward of whether it solves the issue correctly, I don't know if there's like a big improvement. So maybe for hill climbing SWE-bench, I think maybe you can ignore all these things. But yeah, for I guess like a good coding agent, whatever that means, there might have to be more insight. Yeah, cool.
We have time for another quick question. Quick. I'll get the mic here.
So you had a slide on DSPY, and I was curious, are you using DSPy for the thinking orchestration side of the agent, or are you doing more fine-tuned controls for the orchestration of the agent?
Oh, for the DSPy, it's basically an agent that's trained to maintain DSPy or to kind of respond, like hyper-fixated on DSPy. So it has nothing to do with kind of what DSPy itself does, but you can think of it as just like a 7B developer for, like specifically for DSPy. Yeah, cool. Okay, all right, thank you.
Sorry, you should go for the other talk because we're running short on time, but thank you so much, John. Yeah, great talk.